And so today's talk is about battery innovation. I kind of want to start a little bit with the historic side, go to where we are today, and then point towards some new research directions, where we're currently going, and what I think is important in this context as well. So if we look at the battery, it's quite an old concept that started way back in 1799 with Alessandro Volta and the voltaic pile. And then if we look at the now state-of-the-art lithium-ion batteries, there are some big names that also got the Nobel Prize for the lithium-ion battery, including Stanley Whittingham, John B. Goodenough, and Yoshino. There are so many other people that contributed, and also industry has contributed a lot to the fact that we now can use most of the theoretical capacity in the materials we have. And then that raises the question, how do we get to our future batteries with new cell chemistries, more sustainable concepts? Because if we look at the timeline, this is quite long ago, right? Like the contributions from Stanley Whittingham trace all the way back 70 years. So we probably want to be a bit faster in finding new materials. And another aspect that I want to highlight is that batteries, as we know them today, are highly engineered systems. So it is about cell chemistry, but it's also a lot about microstructure design and designing this in a way that it fulfills a specific function. And now we talk a lot about fast charging capabilities. So in a sense, we have this design concept of form follows function, and that rings true here. But we really need to deeply understand the underlying functions at all these different scales. And this is also what I want to touch a little bit upon today. Okay, so the outline of the talk will be, we start very fundamentally with the question, how does a battery work? And touch a little bit about upon physical modeling, to then move on to what's a good battery cell design as we know it today. And that also links back to numerical modeling. And then the last bit will be about how can we design better batteries in the sense of we want to use more sustainable materials. We have a massive material parameter space that we somehow need to navigate. How do we find the right materials? How do we design new interfaces that emerge when we combine new electrolytes with new electrode materials? And what are the appropriate microstructures and cell designs? And in a nutshell, the answer is we need all of the tools we have today, and it's a very interdisciplinary challenge. So we do need advanced characterization to gain deeper insight, but we also need to combine it with physical modeling, numerical modeling, and machine learning techniques that we now have at hand to tackle this quite big challenge, honestly. And I want to start this with a little example and the question, how do batteries work? And I'm quite sure that most of you or all of you know how batteries work. But if you think back, this is an experiment that a lot of people did in school. So we have a lemon, and then you can stick in a nail and you can power a little LED or a clock. And then you can start asking the questions, why does that work in the first place? Do lemons store electric energy? And it's quite easy to falsify that assumption, because if we then actually built this thing and we would use two nails as electrodes, and now we're already introducing some battery terms here, then the whole thing doesn't work. So if we look very closely, we need a nail and a copper coin, and only the combination of these two metals somehow makes the whole thing work. And so then we can go the next step and ask, why is that? And we can play and test around with different materials and then come to the conclusion, is something about the specific combination of components in the system and also specifically the combination of metals. And then this is already where we start to do modeling. We form some sort of concept or idea of how the world works and why it might work. And then we can see how far we get with this concept and how predictive it is. And one idea would be okay, so there must be a driving force for electrons to go from one side to the next side. So maybe there's like a one electrode would be like a shitty home to the electrons, and then they kind of want to move to the nicer side where they see the villa. And so if we now close the circuit, there would be a current going, and all the unhappy electrons would move from one side to the other. There was some animation that is not working anymore. Uh, it doesn't matter much. But basically, as the electrons would move from one side to the next side, and this is a process that keeps going and keeps going, we need to think about our model again, and we realize this is probably not what's happening, because if all the electrons just move from one side to the next side, it would be very crowded in that villa, and that would probably not work with the principles that we expect in nature. So there must be something else going on the very small level. So we can dive into this, or we actually see there are reactions happening. So to actually get free electrons, the zinc on one side needs to dissolve and goes into solution with the juice of the lemon. And then on the other side, we have another reaction happening. And now we realize, okay, the electrons arrive, but they don't stay. They also react and we form hydrogen gas, and that goes out of the system. And that also means this whole concept is not reversible. Now, if we think about a lithium-ion battery that we can charge and discharge, we need to come up with a different reaction mechanism to make the whole system sort of a closed box that is reversible, and so we can go both ways. Now we can use this very fundamental understanding in this sort of modeling concept to then think, okay, now we design our electrode materials in a way that they just work like a storage system. We have some space for the lithium. We can either store it on one side or the other. We can shuttle it between the two electrodes. But we still keep the concept of there's a reaction, lithium goes into solution, the electrons go through the outer circuit, and then we move into, in this case, from the graphite into the layered oxide. And then as we charge it, we can reverse the whole process, and hopefully we can use most of the energy that we put into the cell that we then can take it out again. And so this is very fundamental modeling. And this is what we've been doing for probably a couple of 100 years, is trying to understand how does nature work, and then try to formulate equations that describe this whole principle. So in a sense, physical modeling is describing these very fundamental processes. They are very generalizable. They describe many battery relevant transport processes and reaction processes, including diffusion, electromigration, coupled ion electron transfer. And some examples that you might have come across are the Nernst equation, Butler-Volmer equation. There's a lot of debate. Actually, it would be more correct to describe it in terms of coupled ion electron transfer. And then also for the transport part in the electrolyte, we have concentrated solution theory. So these are all mathematical concepts that kind of describe what we find in the material. And it's based on sort of this reasoning process that I try to guide you through in this little example. Now, the problems are this discovery process is very slow. So there's a lot of try and error. We formulate equations and then we can falsify them, or maybe they stay true over a long time, but it's quite a slow process to formulate new mathematical concepts. And another problem is that the solutions to these equations are limited to very simple geometries. So we have this equation, we can probably solve it for a 1D flat interface where we zoom in very detailed and say like, okay, there's a reaction happening. This is all very flat, no surface roughness. We need to plug in a lot of simplifications to make this whole thing work. And this is sort of a limitation that can be easily overcome if we look at numerical modeling, which is going to be the next part. And so moving on to a good battery cell design, this aspect of complex geometries also comes up here. So we have porous structures and transport, and we kind of need to consider this as well. So if we look at like a standard cell, we typically find a jelly roll, and then if we unwrap this and look very detailed, we find this intricate microstructure. And linking this back to our physical processes, there's a lot happening at a lot of different scales. So starting with graphite particles, we have bulk diffusion, and the lithium moves in between these graphene layers. We do have coupled ion electron transfer, where the lithium ion goes um, into the electrolyte and has a solvation shell and can then move from one electrode to the other one. We do have ion transport, which is described by concentrated solution theory. We have microstructure effects. So, for example, in the separator, we have quite tortuous pathways. So the lithium needs to travel through the microstructure. And the question is, how does that impact our cell performance? And then on the other side, we again have the reverse reaction, but we also have very complicated agglomerates typically in NMC batteries. So we have anisotropic bulk and grain boundary diffusion. And all of this together influences the charging kinetics and also influences the overpotentials in our system, and thus also influences the degradation mechanisms that we can observe. So it's quite intricate down to all the different scales. And so this whole thing is quite complicated. What do we do in terms of modeling? Very often we try to simplify systems, and we do that also in experiments, actually. So if we start with a full cell where we have two porous microstructures, different intercalation kinetics. Maybe there are phase transitions happening in the graphite. We need balancing of the two electrodes. That is super complicated. So what we can do is make it a little bit more simple, go down to your half cell and say, okay, actually, now we have lithium metal that has very fast kinetics, it's a flat electrode. So we kind of get rid of half of the problem. But still, we need to carefully design experiments to learn something about the remaining electrode. And we can do this in a similar way with modeling, or in like the best way would be to combine the two things. I guess the simplest system we can go to if we're just interested in the electrolyte is two flat metal electrodes, and then asking the questions, how fast are the reactions? How fast is the transport in such a system? Um, and interesting enough, there's still a lot of research going on even nowadays. So this is from 2021, where they kind of test or go after the question, does concentrated solution theory, as it has been formulated many decades ago, still hold true in highly concentrated solutions? And then you can try to match the experiments that we find down here with the simulation, and they come to the conclusion, actually, okay, this is a good match, and our theory holds true, and that also means it's predictive, and we can use it in other scenarios. And then adding a little bit more complexity, we can go to the transport of lithium ions in the electrolyte with a separator. So now we add in microstructure, and the lithium needs to move through this tortuous pathway in the pores. And again, we can couple the testing. So this is a very detailed tortuosity determination from impedance spectroscopy. And then you can also model this process. This is one possible software is tau factor, which has been published by Sam Cooper. And that kind of mimics the transport in this tortuous structure. And then we can extract a geometry factor and say, okay, now the transport, because the path is so wiggly and we have constrictions and all of this stuff happening, the transport is by a factor of 2 or 10 or 100 worse compared to the perfect scenario where there's nothing that blocks our way. And then the last bit is adding a lot of complexity where we then have lithium-ion transport in the electrolyte, meaning in the separator and the porous electrode. Then we also have the erection happening and we have diffusion in the active material. Um, and those simulations are accessible today, but they come at a very high computational cost. So we can simulate this at a relevant scale of electrodes. We get very detailed information about the local state of charge or the lithium concentration. But this is computationally heavy because we need to couple so many different physics and go to quite large volumes. Right. What else is important in this context? So this is some work that is going on in the group where I'm currently working. So to go from microscopy data to that we can actually use it for simulation, there's a step that is called segmentation. So we kind of need to label things and tell the computer, this is active material, this is a pore, this is carbon binder. And we can use a lot of stuff that has been developed for machine vision and machine learning to segmentation to get faster and more reliable segmentation methods. So this is stuff that Ronan is working on. Additionally, we often have very different data sets and we kind of need to combine them to get the full information. So it's easier to get 3D data at low resolution from X-ray tomography. It's a bit easier to get a more detailed picture from SEM, but there usually it's much easier to just have a 2D slice because otherwise we need to use FIB cutting and it's quite time consuming to get a 3D data set. So there are actually methods to fuse the data into one large data set, and that is called data fusion, also with machine learning methods. And that is work done by Amir. And this has also been published if you want to look it up. Another interesting thing in this context is it's actually possible to generate 3D structures from just a 2D image. And that even works if there's anisotropy in the system. So if you look at this fiber bundle, we need to have the appropriate cross sections, but then actually the method is capable of producing 3D structures that, if you look at the cuts, are similar to the input again. So this is a lot about stochastics in microstructures, and the specific approach is based on GANs, which is a specific architecture mainly used for image generation. And this can also help to speed up workflows if we now only need a 2D image to then generate a 3D one to then make a simulation that makes it much more accessible, actually. So this is kind of where we are today. We can do numerical modeling based on the physical equations that we or other people discovered before. It generalizes quite well to complex geometry. So now we can look at the microstructure of an electrode and all these coupled transport processes. And we can also link microstructure to the cell performance and ask the question, what is a good microstructure for fast charging or high energy, all these different design questions. There are some problems though. So today's simulations are quite computationally heavy. So if we look at 3D microstructures for like a representative volume element of an electrode, we often talk about roughly 1 day on a high performance cluster using 100 or 1,000 CPUs. So this is somewhat a hurdle because not everyone has access to these computing facilities. And it's also quite long. And you need to ask the question, is the inside gain from a day-long simulation worth this day effort? On the other hand, we have the so-called DFN models. They're simplified models, and they're also known under the name of P2D models. But they work with very severe simplifications. So we assume all the particles are perfectly spherical and homogeneous. Also, the microstructure is just boiled down to a 1D line. We plug in a Bruggemann coefficient. So there's somehow a mismatch between very detailed microstructure simulations and the simplified models. Um, Another problem is actually that these workflows are scattered across very different platforms. So a lot of image processing. So everything I showed, um, like previous work in the group here, is based on Python codes using PyTorch or JAX with GPU parallelization, whereas a lot of simulation workflows are traditionally coded in C++ or even older code like Fortran in combination with parallelization on many CPUs. And then mostly you need high performance computing facilities to then be able to run really large problems. So there's this sort of mismatch, and it is actually quite a large overhead to transfer data from one format into the other and then get it back into Python and then run your analysis. And like just the thing that is scattered makes it less accessible. And another sad thing is that many research codes are not openly available or so badly documented that you can't use them. So I think derived from these problems, what we need is more robust pipelines to go from raw image data to simulation and analysis. In the best case, these are actually tools that the material researchers themselves can use and are not just proprietary to simulation people. So I think there should be a thinking in the way of we can build these tools, but then democratize the access and just make it very easy to use them and accessible to use them. We also need to have faster solvers, and I think it's also crucial to integrate this with machine learning, because at the moment we have this divide between we do either physical modeling or we do data-driven approaches, but if we only do data-driven, we throw away all the knowledge we gain from the physical modeling. So I think the combination of both is quite crucial, especially for 3D microstructures. Okay. And that leads me back to the last bit of my talk and the question, how can we design better batteries? We've seen that this is quite intricate. So they all different kinetics on the different scales. And in an optimized cell, all of the kinetics are on the same time scale. So they are highly coupled. They all play together. And now, if we actually just change one material, we change the whole system. So with new electrode materials, there are new interfaces. That probably also means we need new microstructure. And this is a large design space to then find a good cell capacity, cycle life, and rate performance for such a new system. And that's actually why it's hard and why it takes us so much time to come up with new battery concepts. So one thing we can do is use machine learning and just search faster. So this is one example from fairly recent publication. So a lot of computational chemistry uses DFT calculations to learn something about crystal structures and their stability. And luckily, they feed a lot of their previous calculations into a large database, and that contained 48,000 stable crystal structures. And now, building upon this, they were able to design an algorithm that came up with a lot more materials. So, 2.2 million new structures below the convex hull, which means they should be stable, but it also needs to be tested in laboratories. And what they do is they combine DFT simulations to have the physical grounding with a clever architecture that is based on machine learning to make things faster. And now you find a lot of criticism with DFT simulation, but generally simulations. This is just one example that I came across recently. So basically saying we can also just use a furnace. We have many more atoms in our system compared to a DFT simulation. We roughly use the same power as the high performance computing cluster. There are no approximations, and the results manifest directly into reality. And I think, I mean, take this with a pinch of salt, but it definitely leads us to the fact that we need to question ourselves if the simulation is actually adding value or not. So we need to be very critical, and we need to be mindful of our modeling. I do think a lot of DFT simulations can actually contribute to the knowledge and very deep insight, but just making more and making it larger is probably not the answer. Um, and it also underlines that we always should be combining experimental and modeling work to have grounding of our models in reality. Um, so linking back into the experimental side, there's a lot of initiative to also build these high throughput battery labs for synthesis and testing. This is one example here at Imperial College called DigiBat, that includes material synthesis, electrode preparation, battery assembly, electrochemical testing, and then of course the data storage, and that comes with such a large effort. But we have very similar approaches. Yeah, also, I mean, part of Polis and the Battery 2030 Plus project are these material accelerator platforms. And so I think one push is to speed up simulations with machine learning, but also to speed up the experimental side with this high throughput testing. And that leads me to my first conclusion here is we can navigate this large parameter design space by simply searching faster and sampling more points. This is mostly done with automation, so we need good codes and scripts, or good material handling pipelines. This adds robustness to the system because a high throughput testing facility is probably more reliable in the sense it does the exact same thing again and again compared to a human. We can optimize the search simply because we have more data points. We're probably able to find the more interesting spots and then test these materials. The problems I see are that that is still linear. So we do this thing, we find a sample, and then we do the next sample, and maybe that is better or worse. So in a sense, each sample is always better or worse than the previous best one. But the why remains a little bit unanswered. I mean, we can now run this for, we can do 1,000 searches or 10,000, and then we end up with hopefully good candidates. But maybe we're just missing something because we're not making full use of the information that we could have from the characterization and testing. So tapping into what can be improved and why is it not working, and what are the interesting things, that is quite complicated and also scattered on a lot of different scales. But we can ask these questions. Are there intrinsic limitations on the material side? Maybe it has something to do with microstructure and morphology for this specific material. And what are the material interfaces? Are they maybe the problem? Are there phase transitions happening? Could the electrode microstructure be improved? Is it about the transport pathway and electronic conductivity or ionic conductivity in the system? And then there can be completely other issues on the cell level. But the question is, how can we now integrate this and how can we get this deep understanding of our battery materials? And I think what we should aim for, and this is also sort of where I'm trying to push my research, is embed reasoning with autonomous labs in the sense of if you have a clerk that does his, her work, you better give them really good tools to do that work. So give them a calculator, or in our days, give them a laptop in all the different things that we have. And I think in that sense, we can also integrate all the advanced characterization, but also all the advanced computational tools that we develop and integrate them and just provide them as tools in these autonomous labs. And then humans can use that to do better reasoning. Also, machines can do it to do better reasoning. That also means the solvers needs to be fast, and that links to sort of a term called frugal computing, meaning we need to be efficient with our simulation times and also with our memory. Because otherwise, if we rely on cell simulations that take a day on a high-performance computing cluster, every high-throughput lab would need its own cluster, and that is not sustainable at all. Also, combining machine learning and physical simulations into a more unified framework is really a key piece in this, because we need to move beyond just forward simulations. I'll highlight this in a couple of slides a bit more, but it's basically to eliminate the divide between data-driven and physics-based models. And then once we have this in place, I think we can rethink battery characterization as we do it today. So the assumption of spherical homogeneous particles is so deeply baked into many of our protocols. So if you run GITT and then you apply this analytical formula to extract a diffusion coefficient, this analytical formula has been derived on the very crude assumption that we have spherical particles, and that is often not true. And similarly, we run different experiments for different parameters. So GITT for diffusivity, maybe impedance spectroscopy in with blocking conditions to get some information about the transport in the pore space. But then we kind of throw away a lot of information. And I think using this multimodal data would be, there's so much more richness in the data to do a good parameter estimation using inverse modeling, using combined physical simulations and machine learning, and then embed this in autonomous labs. And just some ways where we're going or where we could be going. I think one aspect is actually developing meaningful models and predictive models. And this is one example from my previous work in Polis, where we were looking at sodium lead oxides and the question, why is it hard to charge them fast and why do they degrade? And so we coupled DFT simulations with phase fit modeling. And basically, what the modeling can give you is very detailed insight into the phase transitions and the evolution of concentration, which is really hard to observe in an experiment. And in this case, as we charge and discharge the battery, we see that the first two phase transitions are happening like a shrinking core because it's a very anisotropic material. But then as we extract more and more sodium, we get a contraction of the material. So there's also mechanics that play very intricately together with the diffusion. And that really limits our performance if we go to higher rates. And so we ran the simulation for different charging rates. And we could see that if we go at very low C rates, we can use most of the theoretical capacity. But if we try to charge or discharge very fastly, we have this limitation that really comes from the material and the combination of mechanics with diffusion at the same time. And what I like about this example is that we also had cell tests at the CSW, and the sort of the simulations were first, and then we had the experiment. So there was no parameter fitting involved to generate this. But so we have a very predictive model that tells us something about very intrinsic limitations in the material. So I think this is one way forward, is developing new models, but also then including this, as I said, this reasoning within autonomous labs in our workflows. So if we sort of have an initial guess of the microstructure, or we have some imaging, we can say, okay, how good is the connectivity and the transport? We can use this to parameterize other models, run a whole cell charging cycle, or we can also model degradation. And now, if we do this and we want to optimize systems, this needs to be fast, right? If we run 1,000 cycles and the 3D simulations are actually one day on a high performance cluster, this is way beyond the time that we can wait and the resources that we have. So, sorry, and basically this would be included in an autonomous lab, there are either human agents or AI agents that then use this to reason and come up with better microstructures. And so this whole idea has been outlined in a very recent publication from our group. Um, and I think the key aspect for me here is this has to be fast so we can actually do it. And so a lot of work also goes into computational performance and using GPUs to make things faster. And some of my work, for example, is about specific surface area. It seems like a very simple problem, but if we actually go to large data sets, there's now 250 voxels cubed, and we have a lot of different particles in here. We're interested in the average surface area or the sphericity of these particles. We need to be able to compute that very fast. And actually using GPUs, we can do that in a very fast manner with wall times that are in the order of seconds. And now the next thing is we also need to push the simulations for like transport and so on into that same time domain. Sort of also work that links back to Polis is connectivity in multi-phase materials. So this is NVP with a carbon network to have better electronic conductivity. The more carbon we have in the system, the less pore space we have. And that also means that the connectivity goes down. So at first, all the pores are connected so we can transport through the system. The more carbon is in the system, the more pores are going to be blocked, and also important pathways are going to be blocked to the point where there's no transport possible. And then I think the beauty of modeling in this context is that we can also give numbers. I mean, it's very intuitive that the more carbon we have, the more pores are going to be blocked. But how bad is it, or where is the sweet spot? So by using simulations to compute the tortuosity factor, we can now say, actually, because of this poor network, and we need to wiggle our way through the structure, the transport is 8 times worse compared to the ideal case. In this case here, it's already 1,000 times or 900 times worse. And then, of course, if there's no connectivity, we end up with a factor of infinity. But that gives us numbers that we can work with. And maybe also ask the question, is it 2 times better? Is that worth 10% more cost? So we really tap into industrial questions now that we can sort of quantify things a bit more. And that pops up in many different places. So also moving beyond spherical homogeneous particles, I think we can do a lot better by actually including the microstructure information and then also combining this with image data so we can use SEM images, label grains, handle the orientations, work directly on EBSD data, and then combine that with GPU computing to ask questions like, how do nanoporous particles behave? How do cracked particles behave compared to the ones that we usually form in the synthesis process? How does that interact with phase transitions happening in these particles? And another aspect, going back to the combination of machine learning and simulations, traditionally, we plug in our simulation parameters, we solve some equations, so we kind of know the equations, but we don't have much access to this, and then we get a result. And then we do the design of experiments. In a very elaborate case, this could be Bayesian optimization that we kind of guess from all the previous results, a good parameter set, and then we do this loop again and again. But a new paradigm that is also shown up is we can actually integrate this into one system. If we code our physical simulation based on machine learning libraries, we get the order differentiation for free, and then we can use this to move forwards and backwards through our physics solver and do something that is often called inverse design or parameter learning, in the sense of we can show it images and try to answer the question, what are the right reaction kinetics or diffusion coefficients for this type of problem? And this is sort of my second conclusion. I think we can navigate this large parameter design space with better informed reasoning, and that ties back to a very fundamental understanding, correlations between microstructure and performance. It's a very active design process. It is cyclic in its nature, and in that sense, each sample contributes to hypothesis testing. So from every sample, we can gain deeper insight and feed that back. And that is a more informed approach to then go with the next better sample.